Okay, so this is the problem we went over in class today, and I'm just going to try and walk you through it. This is my first attempt with this new iPad program, so we'll see how it goes. Here on the first page you have the problem. Just took a picture of it. Just let me know if these pictures aren't good enough. I can probably put this in a different way. But here you can see the problem. So we've got the two blocks sitting on top of one another on the ground, and you just have a force pulling on them. And the first question, which we did in class, is just to draw a free body diagram for each block. And so that is what we'll look at first. So here is your 3 kilogram block, and the first force on it is of course its own weight due to gravity. And we represent that with an m times g. And I didn't put it in here, but the m times g, right, this comes from F equals ma. So in this case, the force is weight, and then the mass would be m, and the acceleration, the a, is the acceleration of gravity. So we put in mg. If you want to see more on that, just let me know. Anyway, and then this is the 3 kilogram block, so it's sitting on top of that other block. So it has to have the force of that block pushing it up, supporting the weight due to gravity. And we call that support force the normal force. Normal means that it's perpendicular to the surface too. So technically you could go in here and draw the little right angle sign down by your thing, but that would be probably a little overkill. And the next force that this block has to have on it, because it is getting pulled sideways as the other block gets pulled sideways, is just the frictional force. And I think I labeled this static friction later because they're not moving with respect to one another. Okay, so that is the completed free body diagram for the top block, or the 3 kilogram block. So here I did put in the explanation of that for the mg. So F equals ma. In this case, the weight is our force, and mass is still just the mass, but the acceleration of a falling body, or the acceleration due to gravity. So that's how we get our weight. And so instead of putting W, you want to get used to putting that mg, as was put there in the earlier one. Okay, here we have our 7 kilogram block. It's going to be a little more complicated because there's more forces acting on it. You've, of course, first got the weight, which we'll put as mg. You've got the normal force due to the ground. You've got the force pushing down on it from the block above, which is equal to mg. I labeled the m sub 3 here, and I just did that to make sure that you don't confuse it with the other m down below. So those are two separate m's. One's the 3 kilograms, and then the lower one is the 7 kilogram. So you always want to be careful in your labeling like that. Now you can leave some of that stuff out, but it can trip you up later. It's just really important that you know what each thing is, and you're kind of meticulous with your labeling. Okay, then we have that force that they show in the main problem, which is pulling the lower block and ultimately the upper block at the same time. We just label it F because that's what they labeled it. And then you have a force in the opposite direction due to the friction of the ground, and that would be a kinetic friction, and they give you that value in the problem. If you rewind this and take a look at that, if you forgot. And then this would probably be the most common one to forget, but if if you remember, you have that frictional force from this block on the upper block, which means you have to have a force from the upper block back on this block. And so that's that static friction in between the two blocks. So this block is getting pushed back, and this block is pushing the other block forward. Okay. And now the next problem is the one where they say, hey, so you got all this, you get this whole block system. Let me try this. So you got this whole block system, right, in the problem. And they go, okay, so if you want this thing to accelerate, that being the whole thing, the 7 and the 3, to accelerate at 5 meters per second, what is the force that you have to actually be pulling on it with? So that's what we'll do here. I can figure out how to get to, alright. So I write my acceleration down there, just so I have it. And of course, the basis of this is F equals ma. But it's so important to remember here that it's the F net, or you got to consider all of the forces that are acting on the block. It's real easy to oversimplify some of these and to get the wrong answer, because you're just not thinking through all the details. So it is F net. The net force, and of course these are just the horizontal forces that we're concerned with. But the net force is made up of two forces on the whole block system. Oops. Sorry, like I said, this is my first shot at this. How did I do that? Ooh. Oh my gosh. Sorry. I'm pushing the wrong buttons here. Oh. I got fat fingers, people. Fat fingers. Alright. So, that allows us to get to this. So the two forces acting on the whole block system, both blocks together, are the force pulling, F, capital F, and then the frictional force of the ground, which is lowercase f for friction, sub g, since it's due to the ground. Now, and that's actually the kinetic friction that they give you in the problem. Now, the reason we don't concern ourselves with the friction between the two blocks is because they cancel one another out as a whole over the whole block system when you consider them both. All right. Now, went through this, but friction is the equation is the coefficient of friction. That little U. It's not really a U. I forget the Greek letter it is. I'll look that up at some point so I don't sound like a moron. But for now, I don't sound like a moron. Times the normal force. And so that can get subbed in there on the other side. And then the normal force is a force. So it has a mass. It's going to be equal to a mass times an acceleration. In this case, normal force is actually equal to the mass of the whole block system, so 10, and the acceleration due to gravity. And so we just do a big substitution here. So I'm going to sub in the mg into the n, and then I'm going to sub the n in for the f sub g, and this is what I end up with. So, at this point, you now have all of the givens and only one unknown, and so you guys can solve this. I won't go through the math on these at the algebra at the end, because you guys can all do that on your own. So, we have the coefficient of friction. That's the coefficient of static friction they give you in the problem. We have the mass, which these are both the same m. They're the mass of the whole block system. So that's a 7 and a 3, which would be a 10. So both of these are 10. The acceleration due to gravity, so 9.8. You guys should probably get used to using 9.81 to be a little more specific. Certainly don't use 10 in these like we did in the conceptual physics classes. And then finally, your A is the 5 meters per second squared that they give you in this portion of the problem. So you just plug in those numbers and solve for your pulling force. Okay. I guess before I do this, let me back up to the question so you can see it all again. And now they ask you find the minimum coefficient of static friction. In other words, just what's the coefficient? How much friction do you need between the two surfaces in order for the 3 kilogram block not to slip off when you pull this at the force we just found, right? If there wasn't enough friction, right, you would just yank the lower block out from under the upper block. They're asking what is the minimum amount of friction you need between these things that doesn't happen and the 3 kilogram block comes along with the 7 without moving. So that's what we'll do here. Okay, so in essence, again, this is an F equals ma problem. We know we have the force. The force we're talking about is the force of static friction between the upper and the lower blocks. And then you have the mass and the acceleration. Of course, we know the mass of the upper block is 3. And we know the acceleration of the upper block will be the same as the whole thing, which is the 5. So we actually have those two values. The trick to this is we're not actually solving for the static friction, we're solving for the coefficient of static friction. So if you recall, friction is the coefficient of friction times normal force. So I'm going to sub that in for little f. And so now our equation becomes the coefficient of static friction times the normal force equals mass times acceleration. And so now we have to ask ourselves, what is the normal force? Well, the normal force between, which is that 7 kilogram block pushing back up on the 3 kilogram block, that's just due to the weight of the 3 kilogram block. So ultimately, we're just going to sub in mg there. So you can see now you have the coefficient of static friction times the mass times gravity, and that's the mass of the little block, so that's a 3. And that is equal to the mass of the little block times the acceleration, which we're going to need of 5. And in this case, unlike what I told you in class where Seth was right, I screwed up on my algebra there. Here it does allow you to just drop out the mass. The mass doesn't actually have anything to do here because it's the 3 on both sides. So to find your coefficient of friction, you simply plug in your acceleration of 5 and your acceleration of gravity of 9.81 and solve for coefficient. And that's that. Explanation over. Let me know what you thought. Like I said, give me some slack though. This is my first attempt.